In this installment, I'm going to introduce you to electrical charge and particle quantities. So let's speak a little bit first about the masses of particles. As we know, there are electrons, protons, and neutrons, and there are isotopes of hydrogen. You're probably familiar with deuterium and tritium, but the single proton version of hydrogen, the mass unit of one, is called protium, because all it has is a proton. So proton, deuterium, tritium. So when we look at the mass of an electron, we have it here in kilograms, in absolute terms. Now in chemistry, we learned to treat, to give proton and neutron one mass unit, one atomic mass unit, because we didn't need to be that precise. But it turns out when we look at protons and neutrons, we do think they have the same mass. Initially, if we look at the ones place, the same, tenths place, the same, hundredths place, the same, but by the time we get to the thousandths place, there is a difference in those two. And when we look at protium, which is hydrogen, we get a different number still. So we have in chemistry been trained to think of protons and neutrons as having the same mass, but in reality they don't, and we can see that a neutron has a larger mass. Well, what do we do if we have an electron that's negative and a proton that's positive? If we could get neutrality, it would seem, if we added them up, if we have -1 and +1. So let's do that. Let's take a proton, and we're going to assign it 1.672622 times 10 to the 27th. Now, this 9.109 times 10 to the -31 is 10 to the -4 different. So whatever we have here, we're going to move 10 to the 4th decimal places over. So that's 1, 2, 3, 4. So 0.0009384. And if we add those up, let me just do that a little more neatly. If we add those up, let's see, we've got 4 and 0, 6, 5, 3, 7, 6, 1. We have 1.6735. $1.6735604. And if we notice 1.6735 is close to the mass of protium. Well, an electron is an electron, and a proton is a proton. But protium itself is a proton with an electron. So it would make sense then, if we took the mass of a proton and the mass of an electron, we might end up with the mass of protium. But it turns out it's not. If we take the two parts and we add them up, we get 67356. 67353. So we take these two parts and add them up, but what we get afterward is less. It's as if I told you that we took one object that had a mass of 1 kilogram and we added it and mixed it with another mass of 1 kilogram, and when we weighed what came out of that, we got 1.5 kilograms. It seems like some mass is missing. There's a defect or a mass defect that occurs. And it turns out we take this thing and we separate it and we get 1 kilogram and 1 kilogram again. And when we combine them, we get 1.5 kilograms. And this is what happens. If we take a protium, an atom of hydrogen with 1 proton, and we mass it, we get this number, 1.673533. But when we get the mass of a proton, we get this number. And the mass of an individual electron, we get this number. So somehow it seems that when we add these particles together, there is a loss of mass called the mass defect. And it is that loss in mass that is involved in this equation. The change in mass that's lost brings about a change in energy, which is a binding energy. And so that's what we have here with the proton and the electron. There's this energy. Some of the mass is converted into energy, which holds the proton and electron together. known as binding energy. And of course, that also happens when we add more nucleons, protons and neutrons, and build larger and larger atoms. It happens with the nucleons too. So we don't need to do any calculations in this course, but I wanted to show you what that really means and the power of that, the power of this part of physics for explaining things. So going through a little bit more here, the PE mass ratio, that is if we take this proton and divide it by the electron. I had said that it's 10 to the minus 4 difference, and that's about what it is. It's about 10 to the minus 4, or 10,000 times larger. This is 10,000 times larger than this. So if we inverted this, we would have about 1 over 10,000. So in any case, the mass of a proton is about 1,800 times that of an electron. Now, just one other thing to note so you have it is there is a universal mass unit, U, in physics. You probably learned in chemistry it's AMU, but that's not really a commonly used term anymore, AMU. It's U, universal mass unit. So 1 U is this many kilograms. 1 U is this many kilograms, 1.66 kilograms. Well, if a proton has 1 U, then that should be the mass of a proton, but it isn't. The same thing is true of a neutron, and that's because the definition of a U is defined as 1/12 of a carbon nucleus. And what we've already seen is that the mass decreases when we put these things together. There's a mass defect. So this number ends up being smaller than the mass we would get of a proton and a neutron. So really fun stuff, and if we were taking an honors physics course or an IB physics course, we would learn about that in detail. Even Regents Earth Science, we would learn about that, but that's not in the AP course. So now let's talk about the electrical quantities. An elementary charge, that is the charge of an electron or a proton, has the symbol E, and its value is 1.602176 times 10 to the minus 19th. It is good for you to know it's 1.6 times 10 to the minus 19th. The units of that are coulombs, which that name is written right here below. 1 coulomb. The charge, Q, of 1 coulomb is 6.241 times 10 to the 18th elementary charges. These two are just the reciprocals of each other. They're the reciprocals. An electron volt is a unit of energy on the scale of electrons, just as elementary charge is on the scale of electrons. A coulomb is in a macro scale, a human scale. Electron volts is unit of energy at an atomic scale. And the symbol for this is energy, capital E, 1.6 times 10 to the minus 19th joules. So this allows us to convert from joules to electron volts. It's just two different units, like feet and inches. One is a lot bigger than the other. And similarly, if we go to the macro scale, 1 joule is 6.2 times 10 to the 18th electron volts. So again, these two are the inverse of each other. And the last important thing to illustrate is we, of course, know the universal gravitational constant, G, which is this number. And it has units of Newton meters squared per kilogram squared. Whoops, that's supposed to be Newton times meters squared per kilogram squared. And now there is also another constant we are going to learn, the Coulomb, or the electrostatic constant. Is the little letter K, not to be confused with the spring constant, Hooke's law, but it's the Coulomb constant, and it has a value of 8.9 times 10 to the 9th Newton meters squared per Coulomb squared. So I'll draw your attention, these units are almost identical. Newtons, meters squared, and the only thing different is it's per kilogram squared and per Coulomb squared. So this is something related to the charge, and this is related to the mass. So when it comes to electricity, charge substitutes and behaves like mass. A little bit more about these quantities. We have these two models of the atom. Of course, we are familiar with the Bohr's planetary model, but really that has been replaced with an electron cloud model, so that the electrons are at any time located, have different probabilities of being located in different locations, like so. So here are all of these electrons. Now, so we want to do a little bit of a calculation type experiment to see what happens here. Let's imagine that we have this atom here, and it should be neutrally charged. So in this column, we have it's what happens when we remove and add electrons. So we're not going to remove any, and so the charge should be 0. If it's gained and 0 lost, it should be 0. So now if we pull one electron out, the charge on this atom, if we pull one electron out, the charge that we have in our hands is minus 1.6 times 10 to the minus 19th. Oh, excuse me, if we put an electron in, the charge would become negative. Negative to the tune of 1 elementary, 1.6 times 10 to the minus 19th. And if we pulled one out, the atom would now have a charge of positive 1.6. Now, instead, if we were to add 2 electrons, this would now have, the atom would now have a charge of minus 3.2 times 10 to the minus 19th. Or if we remove 2, it would now have a 2 elementary, or a plus 3.2. And so you can see then, as we are adding or removing electrical charges, this number, the charge, goes up 1.6, 3.2, 4.8, 6.4, 8.0, 9.6. Same thing on this side. And so here is what's not obvious. Charge exists in discrete exact sizes. So we say it is quantized. It's a fixed quantity. The result then is that all charge is a multiple of E. It is not possible to have a charge of 5 times 10 to the minus 19th coulombs. It's not possible. You have a certain size building block, and the things you can build are only multiples of that size. And so this is where when we get down to the smaller scale, and we've seen this a couple times more in the course, that the universe starts to behave differently when we get down at an atomic or subatomic scale. At the subatomic scale, things become quantized. They become discrete. We cannot have a charge of plus 10 elementaries, or plus 10 times 10 to the minus 18th coulombs. Not possible. It has to be either 9.61 times 10 to the minus 19th or 1.1.12 times 10 to the minus 18th. It cannot be anything in between. And that ends this installment of electrical charge and particle quantities.